This is the project review for Team J2TEC in Senior Design ECE 4960 for the fall of 2020 at Clemson University. Our team was tasked with designing and building an automated Nerf gun targeting system. Our motivation for this project was to gain practical experience with microcontrollers, specifically TIVA and Arduino, closed-loop motor control, computer vision techniques, power management of electrical components, and general hardware and wiring construction. The root cause of our design problem was the complete development of an automated toy gun turret. The turret would be able to target, recognize, and shoot multicolored stationary targets. We set guidelines for ourselves, including that the turret must shoot stationary colored 16.9 ounce water bottles with dimensions approximately 8 by 2.5 inches. This shooting mode would be able to support up to 5 different stationary targets, which would be between 0.5 and 9 meters away from the turret. Any of these targets may be predetermined as enemy or decoy based on the color of the target. Only the enemy targets would be fired at, leaving the decoys alone. The stationary bottles would have cylindrical pieces of colored construction paper wrapped around them in order for each of them to be distinguishable. The decoy targets will be defined as ones colored red. Overall, Mode 1 will interpret data using computer vision and automatically aim and fire the turret at specifically chosen stationary targets. To summarize, our objectives included aiming and shooting at stationary targets, using color detection to identify friendly versus enemy targets. The turret should operate entirely autonomously, and the turret should have a 95% accuracy inside a distance of 10 meters. For our performance analysis, most subsystems performed up to expectation with the exception of motor control. Motor control was at a prolonged standstill throughout most of our project due to an incorrect wiring diagram that we'd received from the manufacturer. After getting past this hurdle, we then realized that both motors only had a single functioning encoder, resulting in us only having the ability to move each motor in one direction. Besides this problem, our computer vision, mount, trigger, and flywheel control, as well as the power subsystems, all performed successfully. The strengths of our project included the computer vision's ability to successfully identify targets and recognize them as enemies or decoys. The dual-axis mount supported the vertical and horizontal movement of the Nerf gun. Our automatic trigger and flywheel control using MOSFET and servo motors was successful, as well as power for the flywheels and for the motors. Our main weakness for our project was the lack of functioning motor control. Given our problem definition, we came up with the following design solution. We would use an Intel RealSense depth camera to identify color and position of our targets. We would then use a dual-axis mount with a 2-to-1 gear ratio controlled by two 12-volt DC motors to move the Nerf gun vertically and horizontally with great precision. We would use 2 different battery packs, one for the flywheel and one for the motor power. We would also use a servo motor to automatically pull the trigger when a target was aimed at. We utilized H-bridges for our motor control and Arduinos for the motor and servo control.
Our computer vision subsystem is comprised of 2 major components, the Intel RealSense D415 stereo depth camera and a laptop running the image processing C++ program. The inputs to this subsystem were the video frames captured by the D415, and the outputs were the pan and tilt rotation angles required by the Nerf gun to aim at the enemy targets. The D415 camera attaches and communicates data to the laptop via a USB connection. The camera was used to collect RGB and depth image frames to be processed in our vision software. Our C++ program relied heavily on OpenCV and functions from Intel RealSense Software Development Kit 2. The enemy and decoy targets were identified by converting the RGB frames from the camera into HSV format, thresholding to look specifically for blue and purple targets, and performing erosion and dilation to filter out noise. Once enemies and decoys had been identified, specific aim points were picked as the center of mass of each of the enemies within the frame. The depth video frames were used to determine the XYZ world coordinates of each of the enemy targets' centers of mass. This conversion from the pixel coordinate plane to 3D world coordinates was done by using functions from Intel's software development kit, and simple trigonometry was used to calculate pitch and pan rotation angles after doing a small shift to make the world origin the barrel of the Nerf gun rather than the camera. Although communication from the C++ program to the motor control microcontroller was not able to be implemented successfully, the C++ program was configured to create data packets storing pan and tilt rotation angles, as well as on-off signals for the Nerf gun flywheel circuit and automated trigger mechanism.
The firing control subsystem is split into two parts. First, we have the flywheel circuit, which is activated by a 5-volt battery source. The flywheel circuit is comprised of the 5-volt battery source, an N-channel MOSFET, a flyback diode, a 220 microfarad capacitor, and a 9-volt battery pack. The flyback diode is connected across the flywheel motor terminals, and the capacitor is connected between the flywheel motor plus terminal and the source of the MOSFET. The flywheel motor terminals are connected across the drain of the MOSFET, and the gate of the MOSFET is tied to the 5-volt battery source. When the 5-volt battery source is switched on, this will activate the gate of the MOSFET and allows current from the 9-volt battery pack to flow and activates the flywheel motors. The second part of the firing control subsystem is the servo trigger circuit. It is made up of a push button circuit, a 5-volt source, the Arduino microcontroller, and a 9 kg torque servo motor. The servo motor is connected to the push button circuit, which is connected to the Arduino. The Arduino is programmed so when the push button circuit is activated, this turns the servo motor 180 degrees towards the trigger and pushes the trigger back enough so that the trigger mechanism can push a dart into the barrel, and at the same time rotating the barrel so the next dart can be fired. The servo motor is attached to the handle of the gun with zip ties. The servo motor returns to its original position after firing.
The two projects are powered by two main battery packs. One is for the turbo DC motors, which is operated by 4 rechargeable batteries 26650 constructed in series. This battery pack has a nominal voltage at 14.8 volts, a nominal capacity up to 5000 mAh, the internal resistance less than or equal 20 milliohms, limited charge voltage is 16.8 volts, and the working voltage is from 11 volts to 16.8 volts. This battery pack can be recharged up to 500 times and has built-in a protection circuit to prevent from overcurrent and short circuit. The other battery pack is for the flywheel inside the Nerf gun, which is operated by 7 rechargeable AA nickel metal hydride batteries, and also constructed in series. This battery pack has nominal voltage at 8.4 volts, a nominal capacity up to 2800 mAh, a limited charge voltage is 9.8 volts, and the working voltage is from 7.7 volts to 9.8 volts. This battery pack can be recharged up to 1200 times when fully or partially drained, and low self-discharge makes it still maintain 80% of capacity after 3 years of non-use.
The motor control subsystem was mainly comprised of two 12-volt DC motors with encoders to control the pan and tilt position of the Nerf turret, an H-bridge circuit for directional control, and an Arduino Uno microcontroller to perform closed-loop position control. The goal of this subsystem was to take input pan and tilt rotation angles from the computer vision program and command movement of the turret to these angles. Both of our DC motor encoders had resolutions of 107.8 pulses per revolution, which was doubled to 215.6 ppr with our mount's gearing. The precision of our motor control system would have been stronger if we had used motors with higher resolution encoders, ideally with more than 1 pulse per degree of motion of the motor. Closed-loop motor control was implemented using an Arduino Uno. A weakness of our motor control was that both of the motor and encoder B outputs were broken, so encoder pulses can only be counted from the encoder A output. Because of this, motor movement could only be quantified in a single direction, and any overshoot in the motor positioning cannot be corrected. Another problem was with the tilt motor, as it was generally unable to hold the Nerf gun at a desired pitch without falling back to the neutral position. This could have been corrected by further adjusting the pitch axle to run through the gun's center of mass, or by obtaining DC motors with higher torque. Since serial communication from the Vision program to the Arduino was not successfully implemented, desired pan and tilt rotation angles, calculated by the program, were manually entered into the Arduino Uno serial monitor to aim the Nerf turret at enemy targets within the scene.
The mount subsystem was constructed using a 4x8 piece of 1/2-inch blonde plywood and a 4x4x8 piece of southern yellow pine with a Lazy Susan turntable ball bearing separating the base from the top. Vertical and horizontal 6.35mm steel shafts were used along with radial ball bearings, shaft collars, and timing chains connected to the DC motors to enable vertical and horizontal motion. The timing chains allowed us to gain better precision from the motors, utilizing a 2-to-1 gear ratio. Plywood was then connected to the top of the Nerf gun, allowing the horizontal shaft to go directly above the center of gravity, limiting torque on our motors. Overall, our group gained experience in several different areas throughout this project. We were able to learn and apply techniques involving computer vision, motor control, automation, and robotics. This project was challenging and beneficial to our futures as electrical and computer engineers. Thank you.